and welcome to Algebra 2 with Mr. Clausen. Today, I'm going to talk about applied linear programming. And to get started, we're just going to go over a real-world linear programming example and look at how the different aspects of linear programming can be applied to a real-world situation. So without further ado, we're going to get started here. Now, what I want to talk about is a real-world problem. What I'm going to do is go through the problem, and based on the problem, I'm going to start by trying to figure out, all right, what is the system of inequalities that I can figure out based on a given statement. This is what we're going to use to identify our constraints for our system and potentially our objective function. Right? And then once we start getting some information down, creating those equations, I think that's the tough part, is finding the constraints and the objective function that's present within the problem. We can graph our feasible region and use the vertex principle of linear programming to go and find out other information based on what's being asked of us. So just to get started here, what I'm going to do is look specifically at trying to create a system of inequalities based on the information provided. So with this given example, we have teams that can be chosen from 30 forest rangers and 16 trainees for planting trees. So right now I can tell you that there is a limited number of these people, and constraints are going to need to be created based on these restrictions. An experienced team consisting of 2 rangers can plant 500 trees per week. All right, so we're going to want to make an inequality based off that. And a training team consisting of 1 ranger and 2 trainees can plant 200 trees per week. So I'm going to want to make another inequality based on that. So we're not going to want to base everything like X being the number of rangers and Y being the number of trainees, because that's not going to really relate things to the resources that we have, especially when we're looking at the production of each type of team. So what I want to do is I want to base everything off of experienced teams, which I'm going to label as variable X, and training teams, which I'm going to label as variable Y in this given example. All right, and some different things that we can take into consideration if we're looking at teams. We can look at the number of teams. That may be helpful. It will be for a number of examples. Whether it is for this one, we'll have to wait and see. But, if you have X number of experienced teams and Y number of training teams, the total number of teams would be X plus Y. But now what I'm going to do is start taking into consideration the limited resources available. All right, so I'm going to look at the number of rangers. All right, and what I'm going to put in this column here are the things that are potentially limited, or maybe something we want to keep track of. All right, so that's why I put number of teams and can put number of trainees. And then in the last row here, let's just go number of trees planted. All right, and with every experienced team, what I want to take into consideration looking at is that an experienced team consisting of 2 rangers can plant 500 trees per week. So what I'm going to do is I'm going to look at this specific row here. I'm going to say, all right, if I make an experienced team, how many rangers is it going to utilize? Well, I'm reading this question. An experienced team consists of 2 rangers. All right, and if we look at a training team consists of 1 ranger, okay? And what I want my equations or my tables to tell me is that, all right, if I choose to make an experienced team, it's going to consume 2 of the rangers, and if I choose to make a training team, it's going to consume 1 of the rangers. And so the equation, if I add all these together, the number can't be any higher than 30, because that's how many rangers we have. Right? Now, if we look at the training teams, what I'm going to notice here is that no experienced teams can be made with trainers. All right. So if you put a trainee on a team, it has to be a training team. You can't have an experienced team with trainers. All right. And then if you want to make a training team, right, you would need 2 trainees. All right. And the total number of trainees that you have at your disposal is 16. All right. And I think an important thing to also take into consideration, because we have this information in our question, is that an experienced team can plant 500 trees per week. All right. So if we have an experienced team, we can just plan on that. So number of trees planted, and I'm going to put per week here because this is an important thing to usually keep track of. But if you make a training team, they're only good for about 200 trees per week. So every training team you assemble is good for 200 trees per week. Every experienced team is good for 500 trees per week. And the total, when you combine all these, is 500x plus 200y. All right, we can just combine all those. So depending on the number of teams that you have at your disposal will tell you the total number of trees that are going to be assembled and put together. Now, what I want to do is from this information, I want to create a set of constraints, all right, things that are limiting me. And one of the things that's limiting me, like I said at the beginning, is the forest rangers and the trainees. All right, so some of my constraints that I need to take into consideration is the number of rangers. And the number of rangers tells me that 2x plus y has to be less than or equal to 30. Okay, and so based on the number of teams, x being experienced and y being training, when we take all the possible combinations into consideration, the number of rangers that are used can't exceed 30. And if I want to make a training team, right, what I want to say is that 2y, which represents the number of trainees here, can't be larger than 16. And so every single one of these type of equations I can go and turn into an inequality. I can take each row of information and try to turn it into some type of constraint. And those are going to be 2 of our main constraints. Now, 2 other constraints I want to just establish here is that x has to be equal or greater than 0, and y also has to be equal or greater than 0. And sitting here looking at it, the number of teams sometimes would be applicable to certain circumstances, but looking at this, there's no situation where I have to make more training teams than experienced teams or anything like that. So we don't really need that first column of information. But this identifies all our constraints that we have. We have a constraint on the number of rangers and we have a constraint on the number of trainees. And by building these inequalities, you take all of those important variables into consideration. Now, the objective function is what you would use to measure how you would make that choice. All right, so previous video we talked about, maximizing some objective function p. Well, the thing that you are objectively looking at is you want to figure out, in this given instance most likely, how to maximize the number of trees that you plant. Now, if you want to create an objective function for this, I would just use, so if you want to create an objective function, I would use t to represent the number of trees, and I would say 500 trees for every experienced team and 200 trees for every training team. All right, and so this gives us some really useful information right from the get-go that we can go and start graphing out some of this information. So let's plot some of this out. We have the limitation of the rangers, and the limitations of the rangers say that you need 2 rangers for every experienced team and 1 ranger for every training team, and the total number of rangers you have at your disposal is 30. All right, and so I'm gonna go and make some tick marks here. Why don't we go 10, 20, 30. And based on that, let's put the y-axis again as the training teams and the x-axis as the experienced teams. And based on this inequality, I could make up to 15 experienced teams or 30 training teams based on the information that I have here. So I'm just going to go draw this line through here. All right, and this is just solely based on the number of rangers that I have, and I could create 0 and 0 for that, and that would be a true inequality. So I'm going to shade this side of the inequality here. And now we're going to take the trainees into consideration here. So the trainees, I need 2 trainees for every training team. All right, and so with that, I know that this inequality has to be less than or equal to 16. All right, and so with this given circumstance, what I'm going to do is I'm going to write this inequality as such. I'm going to write this inequality as such, and just real quickly, I'm going to divide both sides by 2 and say that y is less than or equal to 8. So the maximum number of training teams that I can make here is actually 8 training teams. And so now the main thing that you should be noticing here, okay, plug 0 in for y, use 0, 0 as a test point, we should be able to shade downward here. All right, so now a line representing the limitation of the based on the number of trainees we have, and a line representing the limitation based on the number of rangers that we have. All right, so we only have this quadrant here so far, all right, at our disposal. But I also said that you can't have a negative number of experienced teams and a negative number of training teams. So we're just going to say x is greater than or equal to 0, and y is also greater than or equal to 0. And so that gives us a constraint here, a constraint there, and require us to shade this region. All right, so this whole thing right here is going to be the region that we shade. All right, and this is going to be our feasible region. All right, and based on the vertex principle of linear programming, I'm going to look at the vertices that are made based on this example. So if I look at each vertice here, I have 0, 8. Over here I have 11, 8. And you can graph this in Desmos. That might make it really quick to look at here. At this given point, I have 15, 0. In this point here, I have 0, 0. Right? So these are my 4 points that I can go and analyze using linear programming. So with this, what I'm going to do is I'm just going to test each of these points and see what they do, because the vertex principle of linear programming says that I should be able to look at any of these combinations, and based on these 4 combinations, one of them is going to give me my absolute minimum and one of them is going to give me my absolute maximum. So if I look at my XY pair, I go and I apply that to a given circumstance. I apply it to my objective function of t equals 500x plus 200y. And that's going to give me a specific value for t. So when the xy combination, so 0 training teams, 0 experienced teams, well, that's just 500 times 0 plus 200 times 0. That's pretty easy. Don't need a calculator for that one. That's just going to equal 0. When you have 0 experienced teams and 8 training teams, that'll be 500 times 0 plus 200 times 8. 1600. All right, that's a nice number. I have 11, 8 as another example. So this would be 500 times 11 plus 200 times 8. So in this given situation, I would be able to produce 7,100 trees planted per week. And then the last example I have here is 15, 0, and this would be 500 times 15 plus 200 times 0. And if we do the math here, this would be 7,500. Okay. So if the question simply asks, all right, 7,500, this is my maximum, all right, and 0 is my minimum. These are my points that are the minimum and maximum based on the vertex principle of linear programming. And this is all good, and this is really an excellent way to look at this specific principle. But one of the things I want to point out in this given example is that you may be asked to go and say how many teams should be formed of each type given the information. And if we're looking at rangers and trainees, you can say that this is the maximum, but what you're going to notice here is that this situation uses all the rangers but no trainees. And one of the things I want you guys to start looking at is, what does the information mean when you're going and plugging these things in? And are there things we should be objectively looking at and taking into consideration? So with a problem like this, we could go and we could say, well, if we had 11 experienced teams and 8 training teams, what that's going to use is it's going to use all 16 trainers, and it's also going to use all 30 rangers. So in terms of this type of example, this situation uses all the rangers and trainees. And so if you were the manager of this forestry project planting these trees, even though that this one utilizes the most, even though the 15-0 solution produces the most output in the short run, this solution of 11 and 8 is going to give you a better future output, because the idea here is that, hey, if you have your trainees working, they aren't trainees forever. You don't go work at McDonald's and stay there for 30 years hoping that you just stay at McDonald's. The hope is that eventually you either move up in management at McDonald's, or maybe you move on into a different career field of your choice, but you don't plan on being the cashier at McDonald's for 30 years most of the time. All right, not trying to diss McDonald's, but that's probably not your lifelong goal. And so if we're looking at a given situation like this, this is going to be the optimized solution that you would want to take into consideration. And again, taking that vertex principle, all right, you are going to look at either the minimum, maximum, or more efficient point based on the vertices present. So something very useful to take into consideration when we are looking at all these conditions and variables present. And so with that said, I actually don't have anything else to look at in terms of this particular example. What I showed you is how to go and plot some information, identify some constraints, create an objective function, and then look at a set of data using that objective function. So with that said, I hope that you learned something from this video. And with that said, let's do some math.